All right, so in problem 1.5, we are given this wave function right here. And in part A, we're asked to normalize this wave function. So recall that the normalization property is the integral from over all space of the probability density, or psi squared dx, has to equal 1. And this magnitude of psi squared, all it means is just psi of x and t times its complex conjugate of x and t. And the complex conjugate essentially just flips all of the imaginary terms, the signs of them. So when we do psi times the psi's complex conjugate, the e to the minus I omega t will cancel out with the e to the I omega t that we get from the complex conjugate. So psi squared is just going to be this a term squared, and then this e to the minus lambda absolute value of x term squared. So you're just going to be left with a squared times e to the minus 2 lambda times the absolute value of x dx. And when we integrate this over all space, it should equal 1. So since this integrand is even, we can actually just make this an integral from 0 to infinity and multiply by 2 since it's symmetric. So this is going to be 2a squared times the integral from 0 to infinity of e to the minus 2 lambda absolute value of x dx. We can actually just drop these absolute value bars since we know that x is going to be positive in this range. So integrating this is very simple. So we're just going to have 2a squared times minus 1 over 2 lambda e to the minus 2 lambda x evaluated from 0 to infinity. And we see that the 2's cancel right here. And so we're left with minus a squared over lambda times e to the minus infinity, essentially, which is 0, and then minus e to the 0, which is 1. So we're left with a squared over lambda, and this has to be equal to 1, which implies that a is equal to root lambda. So that is part A. Or I guess we should really just write this out. So psi of x and t is actually equal to root lambda e to the minus lambda absolute value of x e to the minus I omega t. So that is the wave function. And then part B asks us to find the expectation value of x and x squared. So for x, we know that it's just the integral over all space of x times the probability density dx. So this integral is just going to look like lambda times the integral from negative infinity to infinity of e to the minus 2 lambda absolute value of x times x dx. So this integrand is actually odd because this right here is even and then this function is odd. So an odd function times an even function yields an odd function, and an odd function integrated over all space is 0. So the absolute value of x is 0. And for the absolute value of x squared, it's just going to be the integral over all space of this 2 lambda x times x squared dx. Now for this integral, we're going to need to do integration by parts. So first, since this is an even integrand, let's make this an integral from 0 to infinity and just multiply by 2. So this becomes 2 lambda times the integral from 0 to infinity of x squared e to the minus 2 lambda absolute value of x. And we'll just drop those dx. So let's just do integration by parts. We're going to need to do it twice. So we'll let u equal x squared and du equals 2x dx. And we'll let dv equal e to the minus 2 lambda x dx. So therefore v, when integrating, equals e to the minus 2 lambda x over minus 2 lambda. So this becomes 2 lambda times u times v, which is x squared over minus 2 lambda, e to the minus 2 lambda x. This is evaluated from 0 to infinity, minus v du, and v is minus 1 over 2 lambda times e to the minus 2 lambda x. So this is going to become plus 1 over 2 lambda. And there's actually, from the du term, there's a 2 right here. So this 2 will cancel with this 2, and we'll be left with 1 over lambda times the integral from 0 to infinity of x e to the minus 2 lambda x dx. And this term right here is actually, when x tends towards infinity, this exponential term tends towards 0 faster essentially than this term blows up. So this is going to be 0 for the top integrand, or the top limit of integration. And then when x tends towards 0, this term right here just becomes 0, so this whole thing becomes 0. So this term basically goes away, and we're left with 2 lambda times this term right here, so that's just going to be 2 times this integral from 0 to infinity of x e to the minus 2 lambda x dx. So let's just do integration by parts one more time. So we'll let w equal x, and dw must be dx, and then we'll let dp equal e to the minus 2 lambda x dx. So then p equals minus 1 over 2 lambda e to the minus 2 lambda x. So now we get 2 times uv, or I guess in this case wp, which is x times 1 over 2 lambda, negative 1 over 2 lambda e to the minus 2 lambda x, evaluated from 0 to infinity, and then minus p dw, which is just going to be plus 1 over 2 lambda times the integral from 0 to infinity of e to the minus 2 lambda x dx. So now we just have to solve this, and this term right here will go away from the exact same argument that this term went away from. The only difference is that this is x squared and now this is x, but the arguments still apply. So that term goes away, and then we're just left with 2 times this term right here. So the 2 will cancel with this 2 in the denominator. We'll be left with 1 over lambda times the integral from 0 to infinity of e to the minus 2 lambda x dx. So when integrating this, you just get negative 1 over 2 lambda e to the minus 2 lambda x, evaluated from 0 to infinity. So we see that we can multiply this term times this term, and we get 1 minus 2 lambda squared times e to the minus 2 lambda x as x tends towards infinity. That just equals 0, so this first term is 0, minus, as x tends towards 0, this term tends towards 1, so that's just 0 minus 1, so we get 1 over 2 lambda squared, which is the expectation value of x squared. And I will stop here and do part C in another video.